Good morning, everyone. Our topic today is about energy and power. In our circuits, we have components that are providing power or energy, and other components that are absorbing power and energy. Energy is conserved in our circuits. One device or component supplies energy, other components are absorbing those energy. So, in addition to the potential difference, which the voltage that we have seen, it is also useful to know how much is this energy provided, the rate of the energy that is provided or absorbed in the circuit. So, at the end, this rate, the time rate of energy, is called the power. So the power is the energy used per or absorbed per time. The SI unit for the power is watt, and the power symbol is P, and it is the potential difference times to the current for that component. So the potential difference is across this component, and the current is going through that component. So this is the time rate of energy used or supplied. Batteries supply power or energy. They provide a potential increase, potential difference, such that this potential is increased. Resistors on the other side are absorbing the power or energy, and they tend to decrease the potential difference as we have seen. So also the power that is absorbed in those resistors is given by the same equation, the potential difference times the current as the batteries. However, one of them is absorbing, and the second one, the battery is supplying, and the resistor is absorbing. So we seen the expression for the power, delta V times I, and this is from Ohm's law, right? We know that delta V is IR. Now we can use Ohm's law here to come up with more expressions of this power, writing the power in terms of the current and the resistor, or in terms of the potential difference and the resistor. If we take this power and use Ohm's law to substitute the potential difference here, in this case, what do I get? I get this is R I squared. If I substitute the potential difference with IR, I get squared R or RI squared. Or from Ohm's law as well, if I calculate the current in terms of the potential difference and the resistor, and then now substituted I in this expression, then I would get P equals to delta V squared divided by R. So those expressions are useful when I have, for example, the current and the resistance. I can find the power, or when I have the potential difference and the resistance, then I can find the power right away. So let's look at this example here to understand what did we mean by this. If I have a light bulb that consumes 100 watt connected to a wall outlet that provides 120 volt potential difference, what is the resistance? So here I have the power, I have the potential difference. I can right away use this expression, for example, to calculate the resistance. So here I know that R equals to the delta V squared divided by the power, and from there I can calculate the resistance right away. Now let's look at this example here. In this example, we have the circuit. We need to write the junction equation KCL at A. So the current I is to calculate this current. I. So in order to write the junction, the KCL equation at junction A, I can say KCL at A is, if we take the convention of currents entering are being written as negative, leaving as positive, then I have the 3 here as minus, I has I as positive, and I have 1 as minus, and this is equals to 0. You can see that I have 3 branches here that are connected with A, so I'm expecting 3 currents. Then I can find I to be 4 ampere. Then the answer to this question is D. Let's move to the second question here. Using the loop rule, KVL, write the equation for loop 2. This loop, calculate the resistor R. So in this case, I can say KVL at 2 is the following. So here I can see that the direction, the positive direction of the loop agrees with the 3 ampere and also agrees with the I. So I can say now this is minus 3 times 3 minus IR, also minus I times R. I know I just calculated I to be 4 ampere, so I is 4 ampere. Okay, and then the KVL is entering the negative, plus 12, and this is equals to 0. Now I can say this is minus 9 minus 4R plus 12 equals to 0, and then 4R is 12 minus 9, 4R is 3, then R is 3 over 4 ohm. So 0.75 is the answer. Let's see. This question is using the loop rule, the KVL, write the equation for loop 1, which is this one. The electromotive force epsilon here is, so we need to write the KVL for loop number 1 and calculate the electromotive force here. So in this case, let's look at this. Loop 1 is going anti-parallel with the 3 ampere, is going parallel with the 1 ampere. So let me write KVL at 1 as, so anti-parallel, this is positive 3 times 3, going parallel with the 1 ampere, so it's minus 1 times 1. This epsilon is positive because it's entering the negative terminal here, and this is 3 components only equals to 0. Epsilon is 9 minus 1 is 8 equals to minus 8 volt, and the answer is C. Okay, in this question we need to calculate the power provided by the circuit by the voltage source, provided to the circuit by the voltage source. So here we have a voltage source of 15 volt that is connected in parallel with those resistors that are also connected in parallel. So One of the ways to do it is to calculate the current. So we have here this junction, right? This is a junction. Let me call this one A. I can calculate the current. So let's assume that this is I1, this is I2, this is I3, and this one is I tot. So here, in order to calculate the total power, I can calculate those currents, right? And then after I calculate those three currents, I can apply the KCL at junction A to find the I tot, and then the total power provided by the battery would be the current times this voltage. So let's do this. I have I1 equals to 15 volt. 15 volt is in parallel with R1 divided by 250, and then this is 0.06, right? 0.06 ampere. Then I have I2, 15 volt divided by 150, and this is zero point 0.1 ampere. I have I3 equals to I2 equals to zero point 0.1 ampere. So now if I apply KCL at A, what do I have? I have I tot entering, so this is minus I tot. I have all the other three leaving, so plus I1, plus I2, plus I3 equals to 0, which means I tot is the summation of those currents, and this is going to be zero point 0.1 plus zero point 0.1 plus zero point 0.06. I tot equals to 0.26 ampere. 0.26 ampere is the total current. Then the total power provided by the battery is delta V times I tot. And in this case, P is 15 times 0.26, and the power is 3.9 watts. So this is the power supplied by the voltage source. Now, if we want to calculate the power dissipated from the circuit by each resistor, then we can use this expression, which is P equals to delta V squared divided by R, which means if I'm P1 is 15 squared divided by 250, and then P2 is 15 squared divided by 150. In this case, P1 is zero point 0.9 watts and P2 is 1.5 watts, and this equals to P3. Now, if you add them, P1 plus P2 plus P3, it should give you the 3.9 watt, which is the power supplied by the battery. Now here is zero point 0.9 plus 1.5 plus 1.5, and indeed this is, I would say, P absorbed equals to 3.9 watts. So the same power, energy is conserved as we have said earlier. The power or the energy provided to the circuit equals to the energy or the power absorbed by the circuit. Let's solve this example. In this example, we have uh, a switch. When the switch S is open, the voltmeter V of the battery reads 3.08 volt. When the switch is closed, the voltmeter reading drops to 2.97 volts, and the ammeter A reads 1.65 ampere. Find the electromotive force, the internal resistance of the battery, and the circuit resistance R, capital. Assume that the two meters are ideal, so they don't affect the circuit. So we have here very important points that we need to be aware of. Number one, the switch. When I have a switch and this switch changes from one state to another, it changes my circuit completely. It will create a complete new circuit. So when I have a switch here, and this switch was open and then it closed, then I will be getting two circuits. This is number one. Number two, ideal component, ideal voltmeter and ideal ammeter. What does this mean? In ideal voltmeter, there is no current withdrawn by the voltmeter at all. So the current taken by the voltmeter is zero, does not take anything from my circuit. The ammeter, the potential drop across the ammeter is also 0 volt, which means there is no resistance, ideal zero resistance in this ammeter, so it will not consume any energy as well from my circuit. So this is very important to know. The voltmeter will not take any current. The ammeter will not have any voltage drop across. The voltage drop across is zero. It will only read my current for me. Okay, so this is number two. Now let's solve this question. We need to calculate or the electromotive force, the internal resistance, small letter r, and the circuit resistance, capital R. So at the beginning, I will draw the circuit. I have here, as I said, two circuits. So the first one is when the switch is open. I have the following circuit. So I have here the internal resistance R and then the electromotive force. Now the circuit here, since the switch was open, basically it can be removed. It will not affect my circuit. Now it's an open circuit, so the current going here and this circuit now is zero. So the current going into this resistance is zero. Now I will draw my voltmeter. I will draw this one with red, which means this is the positive electrode of my voltmeter. And this one with the black color, which means this is the negative. So here is positive, negative, and this one is reading. So this voltmeter, it's reading 3.08 volt. So this is very important. Also remember that the current here is zero as well. So if I am now to write the KVL, let me take a loop. This is my loop. So if I write my KVL at loop 1, I will be getting the electromotive force is positive because it's entering the negative. And now the loop is parallel with I, so this one is minus R. However, I is zero because the switch was open and there is no current flowing. So this one is zero. Then it's entering the positive terminal. So this is minus 3.08 equals to zero. And the electromotive force is 3.08 volt. So when the switch was open, I managed to calculate the electromotive force because there is no current going into this small letter resistance, which means all the voltage that is on the voltmeter is basically the voltage across the battery coming from the battery. Now let's draw the circuit here when the switch is closed. As I said, I have a different circuit, so start with so here the reading drops to 2.97 volt. So the red is the positive and the black is the negative here. Now I have the electromotive force. I calculated the electromotive force. I know it, 3.08 volt. I also know the reading here. I is 1.65 ampere. I need to calculate this little r and this capital R. Okay. So always remember that the current entering in the ideal voltmeter is zero, no current. So now if I do a KVL, I know this voltage. I know this voltage. I can find the the voltage here, or if I do this KVL loop 2, so I can say KVL at loop 2. So here the current 1.65 is flowing this way. So this is I. So now I have my loop parallel with I, the current I, so it will be written as minus I R. Then I have here the loop entering the negative terminal of the electromotive force, so plus E, entering into the positive terminal of 2.97, so it's minus 2.97 equals to 0. I know I 1.65, so R is this is 3.08 minus 2.97 divided by I 1.65 ampere, and the answer is 0.0667 ohms. This is the internal resistance. Now, if I take KVL here, loop 3, to calculate capital R, then I can write KVL at loop 3. So loop 3 is anti-parallel with I. In this case, I will have IR positive. This is the same for the little r. It is anti-parallel for the little r, so it is plus I r small. It is entering the positive for the electromotive force, which means minus epsilon, right? And then equals to 0. So here I have 1.65 times capital R plus 1.65 times 0.667 minus 3.08 equals to 0. Then R is 3.08 minus 1.65 times 0.0667 divided by 1.65, and in this case R is 1.8 ohm. Okay, so this is how we solve such a circuit. In our last example here, we have the circuit that we just solved. The current, electromotive force, internal resistance, and the circuit resistance are given to me. We need to calculate the power, what power are provided, absorbed by the different components. So let's start first uh, with the electromotive force. The power equals to the electromotive force times the current. Well, this current, which is the 1.65 ampere, is the total current. Remember, again, there is no current going into the voltmeter, so all the current is going through the internal resistance and the circuit resistance, as you can see here. So this is the main current. So 3.08 times 1.65 is going to give me the power provided by the electromotive force, which is 5.08 watts. Now the internal resistance R, I know the value of the resistance, I know the value of the current, so I can use this expression, P equals to I squared R, 0.18 watt. For the circuit resistance, capital R, also I squared R, 4.9. Now if you add those two, it should give you the total power supplied by the electromotive force.